It looks like we have a couple folks still joining in, but if you don't mind, we've got a packed session today, and I'd love to get us started. So maybe I'll give us 1 more minute. Do we still have time, or is it 1:45? It's 1:45. Okay, perfect. Awesome. So hi everybody, my name is Sandy. I am a product manager for AlloyDB. I'm so excited to take you guys through a deep dive today. Joining me here today are Ravi Murthy, our fearless engineering leader. He's the Senior Director of Engineering at Google Cloud, myself, and Joyce, our geospatial engineering lead from Bayer. We're going to go through an introduction just to get us started, give you some of the basics of AlloyDB and some new things that are coming. Next, we're going to do a deep dive into AlloyDB. And then finally, we're going to talk about AlloyDB at Bayer. Aaron's going to come on stage and share with you some of his experiences working with AlloyDB. And finally, I'll give you a what's next, some other sessions to attend, how to learn more. So I thought I'd start us out today talking about why we developed AlloyDB in the first place. You know, Ravi and I have been part of this journey since the very beginning, and it was really motivated by the fact that customers were wanting to migrate from their legacy databases, like, an Oracle, a SQL Server, a DB2, and to standardize on open source databases like Postgres. And as they were doing that migration, they had special needs around wanting more enterprise capabilities, more performance, and more scale. But in the years since we launched AlloyDB, we've seen the market change in really amazing ways. The Postgres community has skyrocketed. Now it's used by 49% of developers. And so what we're really excited about is our opportunity not just to serve those heterogeneous migrations, but also to serve, this amazing customer base of Postgres users who actually often have very similar needs. And we see some common goals for operational databases across both of these customer groups. They want to standardize on open solutions. That means open APIs, but it also means more flexibility in deployments and ability to work with other open source ecosystems and tools. They want to optimize for cost and performance, especially at scale. And then finally, they're looking to build differentiated apps. The markets are changing quickly, and the needs of applications are changing fast as well. And so the questions around how to use your real-time data to do more and build more differentiated experiences are on the top of mind for a lot of our customers. And so in 2022, we introduced AlloyDB for Postgres, a fully managed Postgres-compatible database engine for top-tier relational database workloads. It combines the best of full Postgres compatibility. That means you can really, truly treat it like Postgres, plus the best of Google, bringing Google innovation, especially around things like performance, scale, and availability, to Postgres to help solve some of those problems. One of the things I'm really excited about today is the way that AlloyDB has not only improved performance for these types of transactional workloads, but price performance. AlloyDB offers 2 times better price performance compared to standard self-managed Postgres. And so what you're seeing in the graph here is an AlloyDB 8 vCPU instance can do about double the transactions per minute as a self-managed 16 vCPU instance. And that's because we have a superior architecture with that's vastly more resource efficient than standard Postgres. And Ravi's going to talk to you a little bit more about how that works and why that is. And what that means is now with fewer resources, you have the opportunity to downsize your instance for better performance with half the provisioned resources. Now what you're seeing here is GCE, this is where we're running this benchmark. GCE is cheaper per vCPU than AlloyDB. But when you bake in these performance deltas, your price per million transactions is actually 2 times better on AlloyDB. And in addition to those price performance benefits, it can also offer things like high availability with a full 99.99 no-nonsense SLA, inclusive of maintenance. And that includes really cool features like near zero downtime updates, meaning that you can reconnect to your database right away after we do maintenance. It's also secure and easy to manage. And then finally, in addition to being Postgres compatible, it's deployable anywhere with our AlloyDB Omni product and has a lot of generative AI features baked in as part of AlloyDB AI. We're going to be talking about those a little bit more in detail. And now that's mostly thinking about these transactional workloads. But the reality of building apps today is that the data access patterns are often hard to predict in advance. And when something happens, when your app needs to change, you want to be able to adapt to the new query patterns that you're supporting. And so AlloyDB can offer a single database for operational, analytical, and generative AI workloads, allowing you to adapt and thrive with changing needs for your application. And so it really allows you to future-proof your database because as your application changes, you don't need to move to another more specialized system to accommodate the changes in workload. And in addition to just supporting these different types of workloads, it offers excellent price performance across them. So it's 4 times faster for relational queries, 4 times faster, up to 4 times faster for vector queries, and up to 100 times faster for your analytical queries. And then finally, as I mentioned, AlloyDB is available as our cloud service, which is most of what we're going to talk about today, but it's also available as AlloyDB Omni. AlloyDB Omni is a downloadable version of AlloyDB. It can run anywhere, on-prem, in other clouds, even on your laptop. You can install it with a single command and a Docker container. And that's going to allow you to scale further, more easily operate with some of our autopilot capabilities, and again, build modern applications wherever you are. Now, as I'm sure you've noticed, AI has been a big theme as part of Google Cloud Next. And some of our biggest launches for AlloyDB this year are around AlloyDB AI. AlloyDB AI is a set of features built into AlloyDB, so they're not a different product, they're not available at another cost, they're just built-in features to help accelerate the building of generative AI apps. Now, last year, we talked to you about model access, and we talked to you about vector search. Those are important primitives for building generative AI apps that the database can help with. And this year, we're not only expanding on those 2 areas, but we're introducing a new area of innovation around natural language support for AlloyDB. I'll talk about that a little bit more today, but we have a dedicated session on it coming up later, and so I'll give you the session info for that as well. And then finally, our last big announcement for this year is around Gemini in databases, and specifically in AlloyDB. This is available in preview, and it's about using generative AI to make more assistive experiences in the database, so your jobs around operations and database management are much easier. Now, there are a lot of features here, including code assistance, fleet management, performance optimization, etc. But I wanted to quickly highlight some of my 2 favorites. The first is our new Database Center, which is for fleet management. Database Center works across our database products to provide a single pane of glass for viewing all of your different types of databases. And so if you have a wider fleet, especially a heterogeneous fleet, it can provide a really nice way to elevate what's important and what you should be paying attention to across your fleet. And the second one is AlloyDB Studio. Now, we've heard from a lot of folks that they just want an easier UI for querying their database. And AlloyDB Studio not only provides that console experience for querying, but with features like code assistance, it uses generative AI to make those experiences easier. And with that, I'm going to pass over to Ravi to go under the hood. Thanks.
All right. Thank you, Sandy. So you saw all these very, very impressive results in terms of across a wide variety of workloads, transactional, analytical, Gen AI workloads. Now let's take a peek under the hood to see how does the underlying architecture actually deliver all these amazing results. The first concept here is about disaggregation of compute and storage. So what you have with AlloyDB is a fully disaggregated architecture where the database layer is a set of compute nodes that is running an optimized version of Postgres, and the storage layer is another independently scalable layer of which is database aware and is able to scale out horizontally, and more importantly, independent of the compute head for the database. So because of this complete disaggregation architecture, each of the layers can scale independently and provide a very predictable performance and cost. Let's dive into it a little bit more. So the key part of the AlloyDB architecture is the database-aware storage engine. So this is built on our distributed file system called Colossus, which is a very proven, mature technology. And this storage layer has been designed and optimized specifically for Postgres workloads. So based on the workload patterns, it can automatically scale out and distribute the storage load across a large number of nodes. So that eliminates all the hotspots and the I/O bottlenecks that you see typically with more traditional database architectures. All of that is removed with this AlloyDB architecture. So the storage is a shared regional storage. So all instances of the AlloyDB cluster within a particular region, the primary, the standby, all the read replica nodes, all of them connect to the same underlying storage system. And so this enables a lot of the innovations you will see with AlloyDB in terms of things like read scaling, low lag replicas, fast failover, and a whole lot of more. So just to get into a little more details, let's look at a life of a write transaction. So the application client comes in, writes some data, commits the transaction. So what happens in AlloyDB is at that point, it takes the log records that represent what happened in the transaction and persists it into a fast storage. And once that is persisted, it acknowledges back to the client and the transaction is committed. So as you can see, very little work happens before the transaction gets committed and gives you that really fast throughput, high throughput. And asynchronously, the storage layer takes the log records, processes it, creates the blocks corresponding to those, and is able to give that back to the compute head when needed. And all of those database blocks eventually get stored in Colossus. So a couple of key things to call out here. You're not at all limited by any of the IOPS. So in traditional architectures, you really have to provision your storage for your IOPS. Here, imagine you get infinite IOPS. So you're not limited by IOPS, you're not paying for them. And the end-to-end system, as you can see, is really optimized for extremely high write throughput. And that's why you see the 4 times higher throughput compared to stock Postgres. Now let's look at the read path. So on the read path, we've got the database layer, which is a highly optimized Postgres-compatible engine, and it's got multiple layers of caching built into it. And the layers of caching is the one that enables really low latency, high throughput read accesses. And the data gets automatically cached in whatever layer of the cache as is appropriate. So no knobs, no management, it's all completely automatic and based on the workload patterns. Also, the data gets automatically converted into a format that's best for processing. The open source stock Postgres has a row-based format, which of course AlloyDB also has. But in addition to that, there is a new columnar format. I'll cover that a little bit later. So when you look at the storage engine architecture, what it really allows is you can have as many read replicas as you want, all connected to the same underlying storage system. And that architecture gives you a single endpoint, but behind that, any number of nodes. And it's very easy and very cheap to spin up new replicas, because all you're doing when you bring up a new replica is there is no data movement, no data copy. It just connects to the same underlying storage. You don't need to pay for duplicate storage. But that's really great for your read workloads that can very automatically and dynamically scale based on the load. You can add more read replica nodes and spin them down when you don't need it. Furthermore, because of this read pool architecture, you can send the read workloads to the replicas without impacting the primary workload and the primary performance. So keeping the primary and the replicas separate gives you a lot of isolation benefits. Also, these replicas are very, very low lag. So this is a big deal if you're doing like real-time reporting and querying and trying to get real-time insights. We've made a lot of improvements to the Postgres engine to enable extremely low lag replicas. In open source Postgres, there are definitely many workloads where you do end up with a high amount of replica lag, and the replica may not be able to keep up with the log processing and so on. All of those bottlenecks we've eliminated with AlloyDB with some really clever engineering. And the result is, as you can see in the graph, with very high transactional workload on the primary, we have less than like 25 times lower lag with AlloyDB. But more interestingly, in cases where you also have a lot of reads going on the replica, sometimes open source Postgres is just not able to keep up, and you end up with like an unbounded replica lag. And with AlloyDB, it's bounded and it's really small. So it's really now gives you the architecture to be able to do both primary workloads as well as these read analytic type workloads on the replica nodes. In addition to that amazing performance and scale, what we also provide is enterprise grade availability. This is super important for mission critical workloads. And we've got a 4 nines SLA with like no carve outs, so it's inclusive of maintenance and so on. So within a region, we have fast and bounded recovery for any unplanned failovers. So any unplanned failures, it's automatically detected, and we do the failover very quickly to the standby. And for planned operations, things like maintenance events, patching, or you want to do instance resizing, that planned maintenance operations are truly zero downtime. So it's able to handle this with no disruption to your application. And finally, we have cross-region replicas for things like disaster recovery and so on. Let's dig a little bit on how the high availability actually works. So what the storage engine does is it keeps multiple copies in multiple zones. So you get a RPO 0 for all zone failures. So you get that shared regional storage. And thanks to the architecture, the failover is a bounded operation. There is no applying of logs needed during the failover recovery. And that really shortens the time it takes us to do the failover and bring the standby up and running. And that is something because there's no checkpoints. In AlloyDB, there is no log apply during the recovery path. And when the failover happens, the IP of the endpoint remains the same. So from an application standpoint, things just continue. For planned operations, things where, as I mentioned, you want to apply patches, you want to do instance resizing, there we have a near zero downtime experience. And the way this works is we've got a replacement VM that gets prepared behind the scenes with the new code, with the new instance shape, what have you. And it's fully warmed up before we switch over to the new replacement VM. So from an app standpoint, what you see is connections break, and then instantaneously you reconnect, it works. So you really have that like non-disruptive, truly zero downtime maintenance event. And furthermore, because we pre-warmed the caches prior to doing the failover, you don't get a brownout. So you are back at peak performance right immediately after the switch happens. So that's a pretty big deal. And while all of this is happening on the primary, your replicas continue as is with no impact to any of the replicas. Switching gears for a bit, away from transactional workloads that we talked about, as Sandy mentioned, AlloyDB is really a multi-purpose database. It's a database not only optimized for transactional operational workloads, but it's an amazing database for also analytic workloads and for GenAI workloads. We'll talk about GenAI in just a bit, but specifically from analytics standpoint, the data that's stored in row format for your traditional transactions get automatically converted into a columnar format for analytic and reporting type of workloads. And for GenAI, we've got a vector data type that you can store alongside all of your other data and truly combine vector search with all the other SQL goodness that you're used to. So doing all of this in a single database, real time, super powerful. In terms of the analytic query, we've got this accelerator, as I mentioned, that converts the data automatically from row format to columnar. And we've got a columnar engine that's sitting alongside the row engine that processes these columnar blocks using vectorized execution. So the columnar engine fully compatible with Postgres, so you don't need to make any application changes, no schema changes, no changes to your query. It just runs faster. And the results are identical. So it's fully transactionally consistent and no difference in semantics. So the combination of read pools that I mentioned and the columnar engine really makes it an amazing choice for OLAP, HTAP, and various kinds of workloads without having to do ETLs and so on. And just to wrap up the analytics accelerator, the key point here is no change needed to your applications. It's fully Postgres compatible, and you can use all of the SQL functionality, all of the SQL data types that you're used to. And the system just figures out what data needs to be columnarized and just does it automatically, and then it combines the row and the columnar processing as it goes along. So transparent, super powerful, that's the thing that gives you that 100x faster analytic queries that Sandy talked about. All right, with that, I'll hand it back to Sandy to talk about GenAI and how AlloyDB, in addition to doing transactional analytical, is also amazing for vector workloads.
Thank you so much, Ravi. So yeah, that was really exciting. We got to see some of the basis of AlloyDB and how bringing both Google infrastructure, like a new storage layer, as well as expertise around things like optimizing replica lag, can really make a difference in both transactional workloads and analytical workloads. But you guys are thinking about more than that. You're thinking about how to build generative AI apps, and maybe the database isn't the first thing you jump to when you're thinking about how to do that. But AlloyDB can make that process of creating transformative experiences in your applications incremental by adding a couple new features that are really easy to adopt. And that's because operational databases bridge the gap between foundation models and enterprise GenAI apps. And that starts with an important primitive called vector embeddings. Vector embeddings are numerical representations of data that are created by embeddings models such that similar data is close together in embedding space. And so here's just a quick example where you might create an embedding for teddy bear and stuffed toy. None of the words match from a keyword perspective, but they're close together in embedding space because they represent very similar concepts. And what AlloyDB can do to help you leverage this technology is to turn your AlloyDB into a vector database in just 3 easy steps. The first is with model support, with model access. It's going to allow you to automatically generate embeddings using SQL. And that includes for embeddings on the fly or turning existing columns with unstructured data into embeddings columns. And we have this new model catalog endpoint to make that easier. Next, we have vector search. We want to be able to store those embeddings, index them, and query them. Now, AlloyDB offers up to 10 times faster vector search compared to standard Postgres using the IVF flat index, but we're really excited to offer a new index powered by some of Google's algorithms. And again, this is designed for real-world workloads, because just as we have these analytical and transactional workloads and GenAI workloads, it's not obvious to us that they're independent. Sometimes you're going to run both of these workloads together. You're going to do things like filters and joins to make ultimately your app deliver the best experience. And then finally, we have integrations with ecosystems like LangChain, as well as Vertex AI, and of course, everything's fully Postgres compatible. So let's talk about our new feature around model endpoint management. This is a super simple feature allowing you to register any AI model endpoint in AlloyDB and issue a remote call to that model endpoint using SQL. Now, we support an out-of-the-box integration with Vertex AI, plus a couple third-party models. But you can also connect your own custom models. And we have a specific, again, embeddings function to make it even easier to use to generate embeddings using these models. Now, this works not just for embeddings models, it works for any model you want to call, but we offer a little nice convenience for embedding specifically. And next, in the vector support space, we're going to be bringing 12 years of Google research in approximate nearest neighbor algorithms to introduce SCAN for AlloyDB. SCAN is the vector search technology that's used by many popular Google services. You can think, YouTube or Google Search, and we're so excited to bring it to AlloyDB and Postgres. And I want to take us back, before we talk about SCAN specifically, I want to take us back to what this promise was of AlloyDB. We said we wanted to combine Postgres compatibility with the best of Google. And what Ravi talked about was, again, Google infrastructure, how we can use that to speed up transactional workloads. Or innovation, the ability to respond to a need around, say, faster analytical performance or better replica lag very quickly. And what you're seeing here with our vector search is we got some things from the Postgres community. PG Vector was the first launched before AlloyDB AI did, and we were able to really quickly get that functionality into AlloyDB and take advantage of community innovation to respond quickly. Now we're bringing the best of Google, these Google algorithms, to supercharge that, to make it even better. And so I think it's a really nice story of not just what a specific feature, but what AlloyDB should be, can be. And so this is SCAN for AlloyDB. It's a new approximate nearest neighbor search algorithm implemented as an index type in Postgres. It is fully PG vector compatible. That means you can use it as a drop-in replacement for any existing indexes. And it features, again, the new SCAN index. Now, the SCAN index in terms of numbers is going to offer you up to 4 times faster vector queries, but importantly, up to 8 times faster index creation, making it more possible to actually develop on top of these algorithms, up to 10x higher write throughput on this index, and it typically uses 3 to 4 times less memory. This is all compared to the HNSW index in PG vector. And again, what this means is that it's not just about performance. It's about making these indexes more practically useful for a wider variety of workloads and taking this expertise we have in Google and bringing it to AlloyDB. That's in technology preview, available today as part of AlloyDB Omni. And you can combine this index, these vector search queries, with SQL to create really powerful results. And so AlloyDB is not just doing pure vector search. You can add joins, filters, anything else that's available in the Postgres language to create these really powerful queries. And so here we have just a simple example where you're filtering by price, potentially making the results much more useful for your end users. And AlloyDB AI has started to be used by lots of customers, including Abema TV in Japan. They're not only using our basic product, but they're super excited to use our new model endpoint. to access Gemini Pro, as well as our rapid expansion of vector capabilities. Now, we just talked about vector embeddings, and a really important primitive for working with unstructured data. But there are lots of different ways in which generative AI apps get data from the database to enrich results. Now, I'm sure you guys heard in the keynote people talk about things like data agents, the way in which we query a source of truth database for results. And there are a couple ways you can do that today. The most common of which is a custom tool or API that packages SQL. Now, these are great because they are pretty accurate and they're pretty secure, but they're narrow in scope. You basically need one tool per question or user intent. And so if you're trying to build an app that's super flexible, these tools can add up. Now, on the flip side, we see a ton of emerging needs around more flexible querying, and we see customers starting to experiment with NL to SQL. That's really great because you get flexible querying, but it is not typically secure and not typically accurate. And so AlloyDB is introducing a new paradigm for developing Gen AI apps, which is natural language support. I'm super excited about this one. I'm not going to go into a ton of detail today, but we do have a session later where you can learn more. A couple of the key innovations here are around intent clarification, context beyond our schema, and parameterized secure views. And you can see how that shows up in terms of question and answering. Intent clarification allows you to interactively ask follow-up questions when the database schema doesn't have enough information to answer. There's context beyond the schema. We have semantic knowledge about the data set that's not encoded into the schema, including how different tables are used or the common ways in which we query. And then finally, we have parameterized secure views, which play a really important role in enforcing end-user access control, because you can't trust the LLM to enforce your security. You want to do it at the database level. And again, in summary, a ton of new innovations here. We're so excited to help you build generative AI apps. And with that, I'm going to transition to Aaron to talk about AlloyDB at Bayer. I'm sorry, I left you with a little bit less time.
Old MacDonald had a farm, E-I-E-I-O, and on that farm there was a drone and a tractor with 3 tablets in it and an IoT weather station in every field group. Because farming doesn't look the way that it used to. I'm Aaron Joyce. I'm here to talk about Bayer Crop Science IT, and I'm really excited to talk to you today. We're going to be moving pretty fast because we do not have a lot of time. We've got about 2 minutes to talk about why this matters and about 8 minutes to talk about how it went. Farmers today have a lot of challenges, more diverse set of challenges and expectations than we've ever seen before. Meeting those expectations, providing tailored solutions and expert recommendations for how farmers can use the tools available to them requires a robust global R&D pipeline. The system you're going to look at today and the architecture diagram we'll see in a few minutes are a small part of that robust global R&D pipeline. Providing tailored solutions requires collaborating on a specific set of challenges that individual farmers in a specific area are facing. It means developing multi-year trials to bring those solutions to reality. I'm sure you all are familiar with agile development, with the idea of starting somewhere, evaluating where you're at, and iterating on that to get to a better end result. Agricultural R&D is pretty similar, although where growing plants can take a little bit longer. Now, remember the drones, the tablets in the tractors, the IoT weather stations in the fields? Those tools are all sources of data, and farmers today are using generations of experience to bring that data and make high-quality decisions about effective and targeted use of the resources available to them. That could look like planting more seeds per inch in a particular part of the field based on soil testing. It could look like a targeted field application based on maybe something you saw in a drone flyover. For the system we're looking at today, those decisions are largely centered around crop performance. What that means can vary quite a bit, even in a small context. For example, if we look at a single crop, like soybeans, and a single country, like the United States, the seed you plant and the methodology you follow in Alabama and Nebraska are going to be wildly different. Now, the system you're looking at here is used to store phenotypic observations. If you remember Mendel's pea plants, that's what we're talking about here. Things like the height of the plant, the number of days it took to reach the first growth stage, or the seed that it produced, the grain yield it produced. This data is coming in largely machine-driven, and it's coming from, remember, a global team of scientists that are running a diverse set of experiments relative to their specific context. Two real big things to note about this. One is the Postgres database. We just spent 30 minutes talking about AlloyDB, so you can probably guess what's going on there. And the other is the cycle with the calculations engine. So data comes in to our system, again, machine-driven generally. It's stored in the database. It's delivered out to that Kafka topic as events, and it's published, consumed by the calculations engine, which is a subject for another fantastic talk. It was given at Gopherton last year. The calculations engine uses those events to trigger user-defined calculations, which create calculated values, which are written back to the database. It's a circle, right? Data comes in, it's published, it's consumed, it's calculated, it's written back again. We're going to talk about that cycle in a minute as one of the main reasons that we are particularly sensitive to replication lag. Speaking of replication lag and scaling, coming into last year, we were expecting a lot more traffic, about 10 times the requests, 10 times the transactions, and we needed that to come along with lower replication lag. That's a big ask. When we saw this coming into our system, we started to set up benchmarks. And when I say we, I mean a big we. That whole R&D pipeline that was facing some version of this traffic scaling set up benchmarks for their systems, specific to their systems, to check how they'd hold up to that increased throughput. We didn't pass our benchmark. When we scaled up, we saw replication lag scale also. And the effects of that rippled out through the system that you looked at a minute ago, causing a variety of impacts. So to make a really long story short, we're switching to AlloyDB. Before you call me out, I'm sure that there are ways open source Postgres could have handled this load. We chose to look for other options, and this is the timeline for how we got from where we were to AlloyDB. Let's talk about it. So starting in January, going through about March, we started some proof of concepts for AlloyDB and Spanner. Those are the two tools we primarily looked at. By the time we got to March, AlloyDB was looking really good. It was holding up to that drop-in-place, fully Postgres-compatible claim, and the performance was fantastic. Spanner was a little bit more work. I'm going to have to change the data model. We were going to have to change the code, and our talent was working with Postgres. We've got years of experience with this data model in a Postgres database. We weren't confident we could fine-tune Spanner to get the same kind of performance. So we get to March, we decide we're going to test out AlloyDB. We're going to go further. We spin up a clone of our non-prod environment. We set up a full replica of the system in AlloyDB. Some other stuff happened. We ran the benchmarks. We passed this time. It was fantastic. We were really happy, right? Things are going great. We get to non-prod. We do the same thing, right? Another copy of the system. We're going to AlloyDB. We use the database migration service to clone that over. We learn a lot about the database migration service. We come out of that non-prod migration with a robust checklist of how to migrate our tools, right? It goes really well. Again, it goes really well. We get to production. It didn't go quite as well there. But we got through it, and we'll talk more about the specific things that kind of tripped us up when we got to production in a minute. So, Just a little bit of recap. I'm going pretty fast. AlloyDB, no changes needed. I can attest to that. The performance was fantastic, including the replication lag, which was critical to our system. I want to say that again. The performance really was that good. I've been asked a couple of times, like percentage-wise, how did it rank? It's hard to give a percentage when the benchmark wouldn't finish on the prior system. Database migration service, we're going to recommend that you leave, if you're doing something similar, about twice the length of time that you think that the migration is going to take. So if it's a 2-week migration, leave yourself some extra time. That job, especially in the beginning, has a lot of ways it can crash. And if it crashes, you're starting it over again. It's going to eat up some time. In production, very end of this, before we got to the harvest season for North America, I guess to make a long story short, faster is not always better. Well, it is, but it can cause all kinds of other problems. So race conditions or weaknesses in your database schema, those are things that you can kind of expose when you start to go faster. For us, we have a table called the audits table. It stores a record of things that happened, and we were using it for 2 purposes. We were storing a record of things that happened, and we were storing a record that it was published out as an event on Kafka. So a creation and an update on a table with a pretty large row size, with a table that's getting bigger every single day. This worked. It's worked for years, never had any problems. When we went to AlloyDB in that migration process, we had some problems. After we migrated, we had some more problems. 5 times the speed, design that maybe we wouldn't do if we were doing it again today, didn't work out so great. Easy fix though, we split it apart. You still got that audits table. We split the Kafka publishing out to a separate table with a limited retention. Works great. The reason this slide is here, the reason I want to talk to you about it is I want to encourage you to double check. If you're doing something like this, check your schema, check your expectations. Think about the fact that you're going faster, because we really wish we'd caught this first. It would have been an easy catch and it would have saved us a lot of time. Trying to save you some time by recommending you check your own schema first. In summary, using AlloyDB, we handled 5 times the previous throughput last fall. It went really well. We saw a consistently low replication lag despite heavy load on the writer and reader at the same time. The increased speed drove system improvements. We were starting to become an enterprise bottleneck with this system. As that system gets faster, we expose opportunities for improvement in other places in that R&D pipeline. We get better as a group. It's across the board good. Higher availability of the data set has also been pretty positive. When you go faster, then the people around you are more willing to work with you. When they're more willing to work with you, you've got better collaboration, you've got less duplication. Also a really good thing. I'm going to hand it back to Sandy to close us out.
Thanks so much, Aaron. I love hearing from people like Aaron because they can talk about the realities of doing these migrations and what it means to work with AlloyDB. It might not be the silver bullet, as he mentioned, a 5x increase in throughput can expose other bottlenecks in your system, but it can also be a really important path forward if you're trying to scale or if you're hitting the limits of Postgres. And so before I leave you guys today, I want to share a couple resources and how you can learn more about AlloyDB. So we've got tons of documentation, tons of code labs to learn about the basics as well as some of our new features. I'm going to leave this up here for 1 more second since I see a lot of cameras. And then finally, actually I'm going to skip here. We have a ton of new sessions throughout the rest of Next for you to continue to learn more. And so as I mentioned in the AI section, we've got a great session later today at 3 p.m. about how to accelerate your analytical and generative AI workloads with AlloyDB. My colleague Sridhar is going to be presenting, as well as Sam, with our awesome customer from Neuro, Faye. Second, we've got a session specifically on AlloyDB Omni. This is your downloadable version of AlloyDB, showing you how you can run it in multiple environments. And then finally, again, for those of you who are more interested in AI and Omni, combining them together to create a generative AI app in a disconnected environment, we've got Tabby and Gigi's session on Thursday. So I hope to see more of you guys. Ravi and I are just going to be hanging out outside if you have any questions. But we really enjoyed being with you guys today, and I hope you give it a whirl. Thanks so much.